Honestly, there's like funny memes that I get on my Insta, but I don't wanna like them, because I know like usually will see it.
Yeah.
That's just like,
Thanks.
if I do like them, I do honestly, like for my usual. I like it for the funny, not to be. Um. Yeah. Honestly,
Keep that one on
honestly,
line. He's like,
honestly, the last question, I was a little worried, but like, does he want us to check the info or just something? I checked.
Well, welcome back, folks. Looks like we're just about there. It's official. We're now on just about the last part of the course. This is now week 14 we're in, and next week 15. Our whole goal is just to finish up the last section that we got into on the prior week, and then we're immediately going to convert into reviewing for the final exam. Also, that's got cut off a little bit. I'll be working on grading the third exam starting on Friday, probably going into the weekend. This is the second class I had an exam in, so I'm going to be working on grading this one second. Once it gets graded, I'll be posting the information on right around here on how we did, those kind of things. But any questions at all, folks, with the announcements so far? Not a whole lot of announcements at the moment. Okay, well, we're in a pretty nice part of the class. We're pretty much just wrapping up. We're a couple days behind on the schedule, so it looks like we're not delving too far into chapter 10. We're going to start with section 10.1 on our next class, kind of a shorter section. And then 10.2 is going to describe the calculus on these parametric curves just to see how it all goes. I'll try not to go too far into section 10.2 because we definitely want to be reviewing for the 30th and the 1st for sure. And not spending too much time on the 28th on finishing up section 10.2. But that's where we're at so far. And we've left off right around here, looking into the binomial series expansion as a Maclaurin series by doing this kind of problem once again. So we're going to turn this into another problem where we expand the root of 4 plus x squared to see what we get as an expansion on that one. But before we jump into any of that stuff, any questions at the moment? Okay, let's give this a try. So out of all of chapter 10, I would say this is the problem that kind of makes me uncomfortable. Not this part right here, because running through the derivation, everything just kind of works out. We don't have to be too worried about k. It's allowed to be any real number. We have to worry about this part right here. By definition, the coefficient Cn is referred to as a binomial coefficient, and you might notice on this list right here, the format of this binomial coefficient has a mismatch right at index 0. We don't get a 1 if we plug in, say, 0 for n on this whatsoever. It counts the number of factors into the numerator, and if we put in 0, that would be no factors. We take it as a definition that k choose 0 is going to be defined as 1 in this problem, and it fixes a little bit, but now once we go to actually implement this, expand out the binomial coefficient to see what we get, we have to be even more careful. So here's the problem below that's going to describe how it all goes. Above is just a rewrite of the information we derived. Here is the general binomial coefficient, pretty weird formula. And the binomial series is all of this stuff right here. That's writing out term by term by term, which is not too bad. We see how the pattern goes. We want to write more compactly. That's as compact as it could ever get. But if we want to really expand it out, we take the binomial coefficient, rewrite it like this, and that's where it kind of goes into a wild adventure of expansions, simplifications, and those kinds of things. It's a tough problem, probably not suitable as a real final exam question, but this one might be an extra credit question for folks who might want to give it a try. So if you have extra time on the final exam and the extra energy, there'll be one similar to this one. Well, any questions at all before we give it a try? Okay, and I think we briefly alluded to this. The fun part about this sort of problem is I think everyone's possibly made this mistake maybe at least once in their life by writing root 4 plus x squared This is definitely not equal to the root of 4 plus the root of x squared. It's absolutely not equal to that. But if you made that mistake once, then that makes this a pretty meaningful problem. If that expansion didn't work, what expansion really does work is what we're about to analyze. Before we even get started, let's kind of review how the process begins. This is really, at its heart, a section 11.9 type of problem. We have a formula. It's not the geometric series formula, but something like that. And we have a function. We want to rewrite this function so it fits the format of the actual formula above by taking a 1 over 1 minus something, except that this time in our problem, the format that we want to fit is going to look like that, 1 plus x to power k. So first we match up that form, then we'll know what the k value, the end value is, or not quite the end value, that one's indexed from 0 to infinity. We'll know the x value, rather, and we can go from there. Convergence is just the same as the geometric series as well in 11.9. We just want the absolute value of x less than 1. So here's how it starts out. We need a 1 right where the 4 is, so we just start by factoring. We can factor out a 4 because it is true that the root of a times b is the root of a times root of b. It's pluses and minuses that have messed things all up for us. So factor out a root 4, and you get the 1 plus x squared over 4. Oh, didn't mean to do that. So the part that has matched up now is this part. We have the 1 plus as required. It's also told us what the x value is, but we need a k value. It's just going to be a 1/2, but let's take that extra step to show this. This is now equal to 2, 1 plus x squared over 4 to the power 1/2. So that's the power that's going to go here. That's the power that goes here. And that's what kicks off this kind of pattern that we're seeing all the way through. So next step, let's take care of this part while we're looking at it. Convergence happens as long as absolute value of x is strictly less than 1. But that was for this x. So here we take whatever emerged in this part after doing any factoring, double negation if required, and we'll say that we have convergence for in absolute value, that x squared where the red dot is pointing divided by 4 less than 1, which would then mean x squared is less than 4 after dropping absolute value, multiplying by 4. Then we take the root, and now we have absolute value of x less than 2. So that's our radius of convergence or interval of convergence all rolled into 1. So we want radius, convergence, and well, just wanted the radius. Let's say, therefore, r is 2. That saved us a lot of time. We don't have to use the ratio test on this thing. We can just inherit the part right here from convergence and remap it to our problem. So next steps to take is all about dealing with this stuff right here. Let's rewrite it as 2 coming from that factor that was left outside times the summation from 0 to infinity of k, which is 1/2, choose n, times x power of n. So we get down to this step. Let's actually write this out as a sequence of steps. So this is getting us to step 1. Put it in the right format, but now step 2 is to expand the sum. Then the only reason we're expanding the sum is we also want to expand 1/2 n, the binomial coefficient itself. But there's problems with the pattern if we try to make it fit each and every time. Just like there was problems over here, we had to make that definition happen to get any sense out of what's going on here. Think of this as a step that's going to require re-indexing in a certain sense, like how we had all odd terms deleted or all even terms deleted. This time we have finitely made terms. There just aren't going to be fitting into a pattern, no matter how hard we try. So let's use this information here. General binomial coefficient is defined in this kind of way. And in step 2, we can say root or 2 root Actually, let's start with just the original function. Root 4 plus x squared is now equal to all of this. So 2 times a group with infinitely many terms. And all we're doing on this one is expanding the sum just to get a feel for what do these terms really look like. In other words, we're writing down this information here, just a few terms. So at the first index, when n is 0, we plug 0 here, but then by definition, 1/2 choose 0 is a 1 times x power 0, so just a 1 on that very first term. Then just move on to the next. Let me recenter that index first. Now next, we have a 2 here. The pattern is going to give us k times k minus 1 divided by 2. So go, excuse me, this is n is 0, then n is 1, just one term, k. But k itself is the 1/2. It'd be divided by 1 factorial, which is just a 1, and multiplied by x times 1, or x to the power 1. So that's our first coefficient, or second coefficient, 1/2 times x power 1. This is on index n is 1. And then just rinse and repeat with this pattern. So if we plug in 2, we'll have the k value, and then the k value minus 1. That's going to be the 1/2. Then 1/2 minus 1. This is at n equals 2, so we're also dividing by 2 factorial down below here. And the whole thing is multiplied by an index 2 for x squared on this term. So this is when index n equals 2, we get all this stuff. In front of x squared, that's our third binomial coefficient. Let's see if we can write down one more and then put in the ... dots. But any questions so far with what we've got written in? Okay, so we're now on index n is 3. That means we just take 3 factors right here. If you put 3 right here, you would just get k minus 2, so that makes sense. K times k minus 1 times k minus 2. K is a half, so it's a half, times 1/2 minus 1, times 1/2 minus 2. But you know, these things will simplify on us if we allow them to, so that's going to be part of our work on the next step. This one's divided by 3 factorial, multiplies x power 3, and then on it goes. That's the right power series, but it's now in an expanded form. Our job is to work with this numerator that we're seeing right here and try and see if we can get a new compact form just like this, but simplifying the binomial coefficient is our major goal now. So this takes us now to step 3. Simplify 1/2, let's just write it maybe more generically, simplify k choose n. So if we can get a good simplification on that, we'll have a great way to represent this series. So the simplifying k choose n is going to look like this. It's 1/2 choose n, which becomes first the value k, so 1/2. Then the value k minus 1, 1/2 minus 1, we're looking at right here, becomes negative 1/2. Then k minus 2, that is 1/2 minus 2. But that's just going to be negative 1/2 minus 2 halves, so negative 3 halves next, which would be the simplification of that spot right there, negative 3 halves. But this is starting to establish a pattern. When we do the next term, it's going to be k minus 3, but that's just subtracting 2 over 2 again. So this would be negative 5 halves, negative 7 halves, and so on, until we get all the way down to the line to this part. 1/2 minus n plus 1. So that's the numerator. Denominator is n factorial, and it definitely simplifies. So that's our work on our next step. Any questions to this stage so far? Bring that down just for the sake of needed space on this one. So on the next step, I think it's a good call to simplify this part first. Let's do it kind of like as scratch work. This part is going to be equal to 1/2 minus 2n over 2 plus 2 over 2. So this is altogether 3 minus 2n over 2. So we can simplify that last term. But also, when you look into this, negative appears on this as well. Let's maybe factor out the negative on the next step after the simplification here. We have a half, negative 1/2, negative 3/2 down the line to negative 7/2. Then it goes dot, 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 and 3 minus 2n over 2, all over n factorial. We made one comment on the derivation for this thing here. There's exactly n factors. So that's the comment over here. When we did the nth derivative at 0, we had n factors altogether. It's kind of a small statement, but now it's becoming really, really big, because any factoring that we do down here has to reflect n factors altogether. And look at the factoring we can do. We can factor out a negative sign from n minus 1 factors, because the first one's positive. Also, all n factors are divided by 2. We can just bring 2 power of n in the denominator then. So let's use the fact that on this line, there are n factors. At the same time, there are n minus 1 factors, negative. Taking both pieces of that information into account, we have wipe out the 2 by dropping it down below to a power of the number of factors. So there's n divisions by 2. Let's throw in the n factorial that was there all along. So now those denominators are gone. This one doesn't serve a purpose any longer, but this one we can take into account as our next one. Let's also factor out negative 1 to the power n minus 1. That's the n minus 1 negative signs that appears in the numerator. Leaves now behind a 1 times 3 times 5 times 7, dot, dot, dot. We've also factored a negative sign from here, so this is a 2n minus 3. Almost there, folks. Now, when we take a look into this one, here's another weird double check we have to make. This is a pattern, and it's a pattern indexed by n. And it's not necessarily going to give us all of the right coefficients based on this pattern, as weird as it seems. So we go back up to step 2. I'm going to take a screenshot because our job here is just to eyeball this. Majorly, what's happening at index 0, 1, and 2 is what we're interested in. So referencing what we have down below and using the fact that 2n minus 3 is a core component of the pattern we're trying to establish, let's see what happens at index n is 0. At index n is 0, we get a negative 3, and we're expecting a positive 1. It's not because we did anything wrong. These are the right steps, but there's a pattern mismatch right at that index. Let's say it here in this way. N equals 0 does not give 1 or 2n minus 3. And to clarify, see step 2. We're in step 2, this is what we're checking. And this is the whole value in expanding the sum when our goal is to compact it again. It's kind of a weird step to take right in the middle. Now we check at index n is 1. If we put a 1 in there, we're going to get 2 minus 3, which is a negative 1. Let's see, 1 goes in here as well. Hang on, let me think about this one. I'm expecting a 1/2 at an index n is 1. So if we put index 1 there, I've got a negative 1. 1 here is going to give us a 1/2. So we do have the 1/2 in, but let me double check my work on this one. We were supposed to get a 1/2 on that. Something's gone a little bit awry on my notes here. Anyone see what their issue could have been? I was expecting this one to work at index n is 1, but it appears there's a problem. I'm also looking at my notes down below here. I put in n like that. I wonder if that was correct. So looking into this again, we have n factors on my notes down here. This is supposed to be my cheat sheet if I lost my way on this. I threw in that I factored out -1 power of n. I think I made a mistake on paper down here. I think this is solid. It should have been power n minus 1 because the first of the n factors was positive. So let's move on down the line. Does not seem like we have the right value here. Let's check. Let's say the same. Same for n equals 1, but let's try n equals, hang on, let me look into this again. If index n is 1, that's positive, right? I think we're actually in a good shape. At index n is 1, we have a positive here. Oh, no, but that's the problem. We get a negative. So yeah, that is a problem. Let's try index n is 2 now. At n is 2, I'm going to get a negative sign right here. So negative altogether. 2 here is going to give us 4 minus 3 for a 1. And then over here, for a 2, we're going to have a 4 down below. 2 factorial, and that 1/2 would make a 4. And that is a negative sign that we're looking into. Looks like for index n equals 2, the pattern does start out correctly. So at n equals 2, the pattern is correct. Pattern rather for specifically for the 2n minus 3, giving us the right value for what goes on right here. So just another double check. We plug in n is 2. That means we have 2 here. So we're dealing with a 1/2. 2 here would give us a 1/4. So we have a 1/2, a 1/4. 2 here gives us a negative value. And we do have a negative here as well. So it looks like we do have the right pattern starting at index n is 2. That takes us to the next step. We just now put this all together. So let's call this step, forget what step we're on, step 4. In step 4, we can say that the root of 4 plus x squared, the thing we start out from the very beginning, is equal to 2 times n equals 2 is what kicks off the pattern for us. So we have to put in the very first terms. These are the ones that just did not fit. So it's going to be a 1 plus 1/2 x plus, now the pattern hits, and so we use this stuff from right up here. So let's put in from this step. So I clear out all those screenshots. So this is came in from step 1, a new summation starting at n equals 2, where the pattern got kicked off, go off to infinity. The 1/2 choose n is this stuff that we were writing in. So we can bring in to here, -1 power n minus 1, 1 times 3 times 5 times 7. We could lose the 1 if we prefer, all the way through 2n minus 3. It's then divided by 2n times n factorial, and this x power of n, we take another look into that. Looks like that was a mistake right on that line. That should have been x squared over 4 to power of n, coming from that x squared over 4 right here. So let me carry this step down. Probably not our favorite problem, but the good news is we're moving through this one. So next step, we can say that part right here is going to be x to the power of 2n divided by 4 power of n. And that's where the process finally ends. We did the radius of convergence, which is r equals 2 on this one. And so that's kind of the nastiest Maclaurin series ever. I think I forgot to close a bracket on that thing. But Good news is we can do it. If you want to expand out to root 4 plus x squared, that's the expansion. I might need to come back here to take just another quick look with my mismatch on. I had -1 power of n here. Looks like it should be power of n minus 1, so I might have to come back to this one after class to see if there's any weird touch-ups that have to be done. If I make any changes here, I'll make sure we discuss it when we come back on our Thursday's class. But at the moment, yeah, go ahead. I was checking the values n is 0, n is 1, into the 2n minus 3 part specifically to see if we get the right values on the coefficients 1, 1/2, and this was 1/2 times 1/2 minus 1, 2 factorial. On a second thought, I probably should have simplified these bits as we went to kind of see it a little bit better. But that's where I was checking against the expanded form. Yeah, go ahead.
Is the n plus 1 from that -1?
I think it ought to, yeah, because mainly we're just trying to get it to alternate in sign. So we had n minus 1 factors, then we increase n by 1, it should flip in sign. So if we flip this to n plus 1, let's take another look into that. At n is 0, we'll have that. This is going to be, so here, a negative multiplied by a -3 for a +3. Did give us the right 1, but at least we have positive there on that one. Then we go to put in the 1 on this. A 1 here is going to give us positive. Then a 1 here is going to give us a -1 altogether, divided by 2, so -1/2. We're off on that one, and that's why we're starting off on index 2. But other questions with that so far? Okay, so that's the binomial expansion. This was meant to be applications of Taylor series and Maclaurin series, and this is a pretty honest application as well. But let's turn to the next ones just to see what else we can get into with our applications here. Our next applications are going to be directly citing from table 1. This is typed out verbatim from the textbook of all the important Maclaurin series that we've been looking into along the way. Some of them we've used a lot, like this is in section 11.9. Others were just examples derived in the textbook reading. I think this was derived in a section 11.8 as well. But we'll cite this information as we need it. And if this comes up on a final exam, say any one of these questions down below becomes a final exam question, I'm not expecting to memorize this table verbatim. I'm just going to bake in the right Maclaurin series into the problem. I would say, for example, on this one, use the Maclaurin series for cosine, and I would write it out. So your job on this is to use that information about the Maclaurin series to represent this function down below as just another Maclaurin series, x squared times cosine 3x. Very similar to what we were doing over here, but now we just have way more Maclaurin series we can use for this kind of process. So let's give this a try on example 3 to start this off. Our goal here is to do a couple expansions like that for f of x, g of x. But then we're going to turn it around to integration. The e to the x squared function we mentioned before. And this function turns out is really, really interesting in applications, physical applications in physics, in signal processing, all sorts of weird stuff for odd reasons. But starting at the beginning, here's our next set of applications. First thing we want to do is cite the Maclaurin series for cosine. Cosine at x itself is a sum from 0 to infinity. This one alternates -1 power of n. And anyone recall the power of x on this one? Good call. The thought is cosine is even, and we literally did this. We deleted all the odd terms and just put in even powers. So 2n, divide all by 2n factorial. So using that information, what it tells us is if you want a Maclaurin series for 3x, you don't have to reinvent the wheel on this. You can just put 3x right inside there. Exactly what we did in section 11.9 with the geometric series, like 6 or 7 different examples of that. Other thing we would want to cite is the radius. The radius on this one is infinity. And that's what these instructions are stating. They didn't say compute the radius of infinity, implying you might need the ratio test. State it just means say what it is. But again, this is going to be baked into the problem. We'll just have to use that in your final answer. So this all tells us that f of x, which is x squared, cosine 3x, is now equal to x squared times a sum from 0 to infinity of negative 1 power of n. Something goes in here to power 2n, divide by 2n factorial. The thing that goes into that placeholder is just the 3x that we had in the problem itself. So really not too bad. This is kind of just use the right relevant formula and substitute in the new value for x, whatever it might have been. But we still want to simplify this as we go, so let's keep on going on it. It's next x squared times a sum from 0 to infinity, negative 1 power of n. We can factor this or distribute the power through. You could write this either as 3 to the power 2n, or you could square the 3 and write it as 9 power of n. Completely up to you how you'd like to write it in. And then it's multiplied by x power 2n. Down below it's 2n factorial. So next step we'll take is to take this x squared, bump the power over here by combining the like bases. The Maclaurin series is then a sum from 0 to infinity, negative 1 power of n, 9 power of n, x power 2n plus 2 over 2n factorial. And then this is the major speed up on this problem. We did like all of our hard work in the prior sections, 11.8 to 11.9, 11.10, the first part. But right here, just state the radius of convergence means cite it again. R equals infinity, and we're done. This doesn't require the ratio test. You wouldn't lose credit if you showed it, but this could take up valuable time, say, on a final exam question. Well, we did it, folks. That's the conclusion on that one. A little bit nicer than the prior problem again, but any questions so far? Okay, let's try this out all over again then. Part B next means you would either go to the book, scroll up to get the right Maclaurin series, but just for the sake of attempting to memorize these, the more you memorize, the easier the exam goes. Let's try to write out freehand. Either the x is a sum from 0 to infinity. For sure, there's just an n factorial in the denominator. Anyone recall what the numerator has to be? Absolutely, just x power n on this one. In a certain sense, it's kind of like a deceptively simple representation as a Maclaurin series. X to a power, divide by the factorial of that power, and you've got e to the x, as long as you're adding up infinitely many terms of that. Radius on this one is also infinity. We directly showed that as well in the prior section. So now when we go to write out g to the x, g of x, which is e to the 2x, all we're doing is dropping x into those positions. So this is now a sum from 0 to infinity of 2x power of n divided by n factorial. If you ended the problem right here, no harm done really, but let's take that extra step. It's good practice for when the problems get a little bit longer, when there's extra to do on them, and rewrite this as 2 power of n, x power of n, divide by n factorial, and just state the same radius. Changing from x to 2x gives us the same exact radius of convergence. If it was infinity before, it's now infinity again. Well, any questions, folks? Finishing this one here. Okay, so now in really stark contrast to the very last section, 11.10 part 1, if we're just citing these and re-expressing these new functions of e to the x, it's a really, really fast process, really. And then it gets more interesting because now we can do these kind of integrations. This is one of the integral problems that the author in the reading has cited multiple times and talked about. He often says there is no elementary antiderivative of e to the x squared. So let's work with this one and see what we can discover about it. If this was an exam question, this part being written in the right margin would have been baked into the question itself. E to the x is a sum from 0 to infinity of x power of n over n factorial. And the radius, still infinity. So now we'll take as a first step on this one, e to the x squared replaces that x highlighted in yellow, so it turns into sum from 0 to infinity of x squared power of n divided by n factorial. Then we can simplify this a little bit further, and this time it's not just a good idea, it's practically a requirement, because we're going to integrate as well. We don't want to try to do a whole bunch of expansions and then integrate at the same time. So let's simplify this down to from 0 to infinity. This is just x power 2n. Those exponents would multiply, divide by n factorial. And just for emphasis, changing from x to x squared did not influence the radius whatsoever because it was infinity on this one. Because it was infinity, still infinity down here on this one. You might notice the times the radius does change is when you go from this, radius 1, if the radius is finite, and then you go from, say, an x to an x over 4, that absolutely did change the radius. It became 4 itself. The only reason it's not changing on these problems is specifically because it started as infinity. Put in x squared, 5x, anything like that. From infinity here, we would get infinity down here. But now we can integrate. Any questions before we go to that last step? Okay, here's how it goes. There's no elementary antiderivative of e to the x squared, which means you can't actually write down the antiderivative without fundamental theorem of calculus part 2, or without using infinitely many algebraic operations, infinitely many exponentiations, multiplications, additions, and subtractions, essentially doing this right here. That's a requirement to getting the antiderivative. So we'll write out e power x squared dx is now the integral of this Maclaurin series, which is a sum from 0 to infinity, x power 2n plus 1 over n factorial dx. And you could show an extra step on here if you like, where the integral sign moves inside. But if you want to integrate right at this step, that would be completely fine as well. There's that additional step just for emphasis if folks like to visualize it this way. It's still a sum from 0 to infinity, and we can rewrite this as 1 over n factorial. Integrate just the part that's indexed by x. X to the power 2n plus 1 dx. So the whole integral sign moves through infinitely many terms, settles on integrating that one thing that involves variable x. And that's really fast in this form, or either form we're looking at it really. Here's the easiest thing to miss though. If we're doing an antiderivative, we're looking for a family of antiderivatives, the most general form. So we put in the constant of integration c. I usually put it in first. Then put in the sum, going from 0 to infinity, of n factorial is still in the denominator. When we integrate this, we can push it back into the numerator. It's going to be x power 2n plus 2, going up by 1. So now we have to divide by 2n plus 2, that new exponent, and we're on our way. Yeah, go ahead.
Did 2n plus 1 too early?
Uh-oh, I have 2n plus 1 here. Oh, yeah, that's already integrated. Thanks for spotting that one. That should have been a 2n coming from right there. A little color coding can highlight that weird error. So we're integrating the 2n. And then finally, thanks for spotting that one, 2n plus 1 right here. I must have been thinking about integrating, but just a little too early, like you said. Whatever that was, 2n plus 1. 2n plus 1. I think the computer is just tired. It's been a long semester. But with that correction, we have the right power here, and so the right denominator down there. Last thing is just to state the radius of convergence. But even after all this work, we inherit r is infinity, even after integrating. So there it is, radius is infinity. That's kind of a weird one. Any questions, folks? Getting through that one there? Okay, well, we've found e to the x squared a couple ways now in this course. We did it once with the fundamental theorem, but then we said if you use that fundamental theorem, you now have to use Simpson's rule, trapezoid rule, to approximate the integral that you would get. But here, This is really, really fast convergence. Sure, we don't have a closed form for the antiderivative, but if we ever needed to evaluate it, it doesn't take too many terms right here to get high accuracy because of the factorial. Well, let's try this out one last time. Sine x divided by x. But any questions first? Okay, this one's a little bit weird, and it has the same feature. There's no elementary antiderivative for this one. If this was false, that statement, people would be very, very interested in your antiderivative because this function is such a special function that it's used all over and applied to mathematics, physics, engineering, signal processing. The list goes on and on and on. And this is like really hardcore applications. We're talking about wave propagation, light scattering, all sorts of those really tough looking physics type problems that we're dealing with. Based off this integral, this is all over the place. It's kind of like Euler's number. So if we need to deal with that, we need a good handle on it. The first thing we need to solve is the antiderivative. We'll cite the sine function as a Maclaurin series. Sine x is a sum from 0 to infinity. This goes -1 power of n, just like cosine. X power 2n, except it's an odd function, and 2n plus 1 is our representation of an odd integer. Divide by 2n plus 1 factorial. And radius on this, still infinity. This time we're taking sine x divided by x, so there's a little bit of an extra step to take on that. Let's rewrite sine x in this way. Sure, we have an expression over here, but that's really, really abstract. And if you do anything algebraically with this, sometimes it is a good idea to expand. Let's put in index n is 0, so we'll get positive here, and we'll just get x. Divide by 1 factorial at 0. At index 1, let me back off that step, we get a negative sign, and that would give us x cubed. Down below, that'd be 3 factorial. And this is the pattern for the sine function. It's only odd terms. We required that with the power that's being expressed here. Put in index 2. It's not only just odd terms, but it's also alternating. Power, or index 2 gives us power 5 on this one. So x power 5 over 5 factorial, and so on. So if we take this and divide the whole thing by x, as we need to because of that part right here, this all gets divided by x, and, well, that means it's now a 1 minus x squared over 3 factorial plus x power 5 over 5 factorial minus, and so on down the line. In other words, it's no different than what you have up here. Oh, thank you, x to the 4th on that one. No different except the power went down. That power 5 should go down to 4. Thanks for spotting that one. So this tells us finally sine x over x is essentially this, but with power 2n up in the numerator. So it's a sum from 0 to infinity, -1 power of n, x power 2n, divide by still 2n plus 1, factorial. And that's not too bad to integrate. We can integrate that one just like we did the last problem. So let's say here in a fancy way, therefore, the integral of sine x over x dx is the integral of a sum from 0 to infinity, same as a step above. And dx goes there, just looks kind of funny having that weird structure inside as an integrand. Throw in the constant of integration c, just so we don't forget it, and then plus, now a sum from 0 to infinity of -1 power of n. Here, this is the only thing influenced when we integrate. X is now to power 1 higher. 2n plus 1. This kind of feels like deja vu, but we integrate at the right time this time. 2n plus 1 factorial down below. And last statement, that antiderivative is as a power series, valid with radius of convergence still infinity, coming from that original statement way up here. Oh, absolutely. I think I just forgot that denominator. So 2n plus 1 factorial times 2n plus 1. Thanks for the insistence on those weird mistakes so far. The omission was that power divides there. Looks like I put in the factorial, then felt like it was all good from that last step. So we've got it, folks. That's another power series representation for a weird integral. That one is special. It's literally called a special function in mathematics, and there's a whole bunch just like these. They're functions where they don't have an elementary antiderivative whatsoever, yet their use in applications comes up over and over again. They have to be studied and given names at all at the same time. So there's names for these integrals as well that we're going to take a look onto in the next page. But any questions so far with the last step here on the computation? Okay, so the next thing is just a block of text. Because this is meant to be an application section, I felt like we should talk about some of these applications. What we were saying about an elementary antiderivative is defined here. It's a function when we have an elementary antiderivative. It's a function that can be used with a finite combination of ordinary arithmetic signs and your typical functions, such as the polynomial functions, the root functions like cube roots and so on, trigonometric inverse functions, and so on down the line. If you can write down a function with finitely many terms involving those, we call it an elementary function. But we keep on saying certain functions have no elementary antiderivative whatsoever, and some of them are classified as being special functions. That's literally what they call it. A special function in mathematics is one that is not elementary in its antiderivative, but it shows up just all the time. This one, sine x divided by x, is called the sine c function. Kind of a weird name. And this one is an integral, gets converted into this one, and it's called the sine integral, or abbreviated as just the SIX integral. If you've ever played around in a computer algebra system and tried to integrate something weird, sometimes these are things that just show up. SIX, or there's a whole huge classification of these kinds of special functions. But SIX, like is mentioned down below, is used in my examples I put down: light waves, sound waves, quantum field theory, all sorts of things can come up with that function there. So if you're curious about these applications, if you know you're going to take a lot of physics, here's one of them. Said control click was going to work on that. That was a lie, I guess. Control click. It did something. There it goes. So here's the diffraction and imaging application with the SIX integral using the sine c function. And essentially, this is what it's trying to solve. These kinds of problems with optics. Diffraction patterns of width w involves a mathematical sine c function. There it is. We're using z on this, sine z divided by z. And we're looking at some kind of diffraction pattern through a slit right here. The light goes this way. And somehow, some way, I'll leave the reading to you folks. This function is fundamental in solving this kind of problem with just light diffraction patterns. So out of nowhere, this problem that feels like it's just a mathematical curiosity is solving all sorts of real world phenomenon. The one in the link right here was just one where I could get an actual diagram to show to class and some of its uses. It takes some time to actually read through all this and what's really going on with the sine c function. But if you have a background in physics or you know you're about to have one, this is some pretty good reading to take a look into. Looks like, yeah, some weird quantum field theory is probably what we're looking into if it's a double slit experiment. So it looks like it's getting into diffraction, quantum field theory, all sorts of pretty heavy physics, all from just that function and the SIX integral. So it's not the best application because we need to load like, I don't know, about 30 credits worth of physics to really appreciate the application. But at least we know where all this stuff is actually going. So instead of solving that one, here's another application we can solve. Absolutely. So we can solve a differential equation problem. And that makes it a good exam review question just all on its own, right? We can expect something like this to show up. This problem here is from section 9.5. We mentioned before, differential equations like these arise all the time on just simple situations in differential equations describing other real world phenomenon. So we need to know how to solve these kind of problems as well. It's y prime plus 2xy equals 1. Because the coefficient is a 1 right here, that's a critical check we have to make. It tells us that that function is the p of x function. P of x equals 2x. Then we need an integrating factor as our next step. We go over there, grab I of x is e to the power of the integral of p of x. We're not looking for the world's most generic integral this time, just the most simplest one will do the job. We'll set the coefficient c to 0. So this is e to the power 2x integrated. That was meant to be a substitution step. E to the power of 2x integrated right here. So then e to the x squared comes up in this problem. Almost unfortunately, right? But we have an extra tool to use against on this. The next step we take is grab e to the x squared, the integrating factor, and multiply both sides of this equation by that factor. So we now have e to the x squared y prime plus 2x e to the x squared y equals 1 times e to the x squared. Just to emphasize, also multiplied here. If you wrote in e to the x squared, that would have been great. We also did a big check each time we did this. The only reason we had to do the integrating factor is because the coefficient 1 here doesn't solve the property that the derivative equals 2xy. The derivative of the coefficient 1 is 0. But if we differentiate that and use the chain rule, arrow is just saying this is the derivative d by dx, you do get this. Derivative of e to the x squared is e to the x squared by chain rule times 2x. That means our integrating factor step worked out correctly. And our new line is pretty crazy. This is always interesting to look into. We are reversing the product rule, literally reversing it into e to the x squared y times y prime. Just double checking the logic since it's been a while. If you did the product rule on this line down below, you might differentiate this first and copy the opposite factor, which is what's done up here. If you did that, you have to copy the y factor highlighted yellow and differentiate the e to the x factor. But we validated that is the right derivative here. So with the product rule reversed on the right-hand side at e to the x squared, we can integrate both sides simultaneously. Integrate the left with respect to x and integrate the right-hand side with respect to x. And we get that e to the x squared times y equals constant plus antiderivative of e to the x squared. But if this ever happens, like say, maybe on an exam, if any result that you derived or computed on an exam is relevant, just cite it, grab it, and use it. We've already integrated e to the x squared once. We don't have to do it a second time. So we're just going to put in that result. So from that temporary citation here, it's going to be the constant plus the sum, and goes from 0 to infinity, x power 2n plus 1, n factorial times 2n plus 1. And just for the sake of expressing what values this convergence is good for, the radius of infinity also applies on this equation here. So all I did is directly cite this problem we did earlier, substituting integral e to the x squared. Any questions with that substitution there? Okay, that means we pretty much got it. This differential equation, which can describe a lot of pretty simple situations, has solution that goes y equals, I'll multiply both sides by e power negative x squared. And then it will multiply c plus sum from 0 to infinity, x power 2n plus 1, n factorial 2n plus 1 with the same radius, r is infinity, is the valid for convergence on that solution y. Not the best way to write a function, but again, the approximations here are highly accurate. If we need a function value, it doesn't take too many terms to get that value. And using computer software to just program what that value, what that series is right here, all of this could be sped up a massive amount for even better accuracy. But any last questions, folks, on solving that differential equation? Definitely a more attackable kind of application we can solve rather than dealing with, looks like quantum field theory for real on this one, the double slit experiment. But last application we'll take a look into for the night is going to be this one. Really, this problem is kind of a famous equation that results when you get this equation down. E is Euler's number, same number we've been using long before. But now out of nowhere, we're also dealing with complex analysis. We're going to deal with the complex unit, I equals square root -1 on this problem. The claim is that e to the power of I times x is somehow a combination of cosine I sine x. Out of nowhere, this is really unexpected. But if you take lots of calculus, eventually complex analysis will come up, and this becomes a really important equation right here. Sorry, say again? Yeah, it could be used in Fourier series. This is sometimes referred to as the polar form of any complex number. Write down any complex number, like say 4 minus 3i, and a bigger question could be, what does it look like back in this format? Because this is just such a useful representation. So it's used again all over the place. Fourier series is a great example of that. To get started with this though, really it's kind of a review problem. We start with e to the x. It's a sum from 0 to infinity of x power of n divided by n factorial. We also need an expansion for cosine x. That's from 0 to infinity of -1 power of n, x power 2n, and then 2n factorial down below. And then lastly, we need sine x. This one from 0 to infinity, -1 power of n, x power 2n plus 1 over 2n factorial. And now the next step, which is familiar, just looks weird, is whatever goes here for x also goes there. So if we're doing e to the power of ix is going right inside here. I can't use the whole equation since we're trying to show it's true. And I want to start on the left-hand side, moving it into the right. Left-hand side is e power of ix, which means it goes right here. So sum from 0 to infinity, ix power of n over n factorial. But to see this problem really well, we also need to expand. Yeah, go ahead. Oh, thanks for spotting that. Yeah, we should beat that horse a little bit more for sure. 2n plus 1 right here. Thanks for spotting that one. Other questions at the moment? Okay, let's keep on going with that. Thanks for spotting those factorials. What we want now is an expansion, what's here on the red dot. So e to the ix, starting at 0, that's just going to give us a 1. Then we start incrementing. We're now at power 1. We get ix over, well, 1 factorial is not too interesting. Let's just leave it at 1x. Now at power 2, ix squared over 2 factorial. We do need a bunch of these. Let's go up to maybe power 8 or something like that. It's a little bit tedious, but we need to do these computations. Ix power 3, 3 factorial, power 4 over 4 factorial, Ix power 5 over 5 factorial, Ix power 6, 6 factorial, ix power 7 over 7 factorial. Let's make this our last one, ix power 8. 8 factorial. You know what, one more. We have just enough space, ix power 9 over 9 factorial. And plus dot, dot, dot. Just as a reminder, this goes forever. Now, I is square root -1, but look at the role I takes. It's going to go right here, attached to all the sign terms. So it's here, 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 here. It's everywhere, but somehow, some way, it has to stick to sign, which means I has to just survive on every single one that involves an odd power. So here, here, and I'm glad we got power 9 on there. We need to re-express all these involving just I itself, even though there's an I cubed. That's not so bad. There's a great way to write out powers of I. This can be written in as 1 plus. This I is okay right where it is. So ix is fine. Plus. Let's back off on the plus. Anyone recall what I squared should be? Absolutely. If I is root -1, I squared itself becomes -1. So this is just negative x squared over 2 factorial. That's right. It's just a quick note. I squared -1. Over here, it's I cubed. But if I squared is -1, I cubed is, what would you say it ought to be? Exactly. All you're doing is taking this equation, multiplying both sides by I, so that I cubed on the left is -I on the right. So go minus I, leaving behind x cubed over 3 factorial. Let's highlight the power as well, because we're looking into the sign terms the moment we see a power of I and an odd power on x. The next one, multiply both sides by I, we get I power 4 is -I squared. But I squared is -1, so that's +1. We have double negation. And so on our next term right here, this is just a 1 times x power 4. I'll write it in as x power 4 over 4 factorial. Now it starts to repeat. If we multiply both sides by I, we get I power 5 equals I on this one. So this computation is I power 5 is I, and now I is starting to show up. We go plus I again, times x to power 5 over 5 factorial, and rinse and repeat. Multiply both sides by I over here, we have I power 6 equals I squared. Moving back, we know I squared is -1. So I vanishes on this, just leaving behind a negative sign. So we'll go negative x power 6, 6 factorial, and then more terms. I'm running out of space to put in these little descriptions, but we multiply this last equation by I, we get I power 7 is just -1 times I. So -I, x power 7, 7 factorial, and 2 more to go. I power 8 is exactly I power 4, just comes out as a 1. Multiply both sides by this, I power 7, the -I, by I again, that's -I squared for a +1. So I vanishes on this one. It's just going to be, let's see, negative x power 8, 8 factorial. Then last one over here. I to the 9th power is going to be positive I altogether, x to the power of 9, 9 factorial, plus, and then infinitely many more terms. But from here, we're pretty much done. Let's take a look at what we've got. Oh, let me double check. So we were taking I power 8, which is the same as this one. Yeah, that one should have flipped to positive right here. If I'm looking at my terms, that's kind of the pattern, right? We went positive, positive, negative, negative, positive, positive, and so on. So positive, positive. Really what I should say on that last bit right there is minus, just as a reminder, it's going to be negative, negative on the next two and so on. Thanks for spotting that one right there. So final thing, look into all the powers that are even. It happened here. It also occurs right here, except that's x power 0, not visible, written in. But everything that's an even power is just an expansion of cosine. When we expand that out, we do get for cosine the 1, then x squared over 2 factorial, x power 4 over 4 factorial. So at this stage, we have e to the ix equals 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x power 6, 6 factorial plus x power 8, 8 factorial. So that came from every term that didn't involve I. Every other term does involve I, so that just means it factors out. Plus I times. When we factor out that I, we have an x on this one. Over here, minus x cubed. Then over here, plus x power 5. So not only is it alternating, not only is it starting at x, but it's the exact same terms we see from sine x. And we expanded that one on the very last problem it looked like. So last one is going to be minus x power 7. Let's not forget the factorials. Over 5 factorial over 7 factorial. Plus x power 9 over 9 factorial. I should put a plus dot 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 on both of these as just a reminder. That's infinitely many terms. And so we have now a conclusion. E power ix is, this one has even terms for cosine x, plus I times, only odd terms on this one, so we'll say sine x. So that's our weird formula. This is the polar representation of a complex number. Other things done in complex analysis is just take any complex number and rewrite it in that format. But also gives you kind of a cool conclusion as well. You can write out this famous equation, e to the power I times pi. E to the power of I times pi is going to be cosine pi plus I sine pi, which becomes e to the power I times pi is -1. Kind of the weirdest equation ever because it takes Euler's number, it takes the complex unit, it takes pi, wraps it together with a -1 somehow, some way. Other people prefer this equation, e to the pi x plus 1 is 0, because now you've got the multiplicative identity, you've got the additive identity, just a whole bunch of stuff in one equation, and it's a true equation. Complex analysis is weird, but that's where a lot of this calculus starts going towards, because a lot of our methods just require these extra tools down the line. But any questions at all, folks, getting down to that last derivation? Well, we got through it, folks. Thanks for all the help with those denominators and factorial issues. When we come back next time, we're switching gears completely and now looking into chapter 10. It'll feel like a kind of a nice break. We'll look into old calculus methods from calculus 1 even, things about tangent lines, integration, but in a whole different kind of setting. But have a great night, folks. We'll take a look into those next class.
Sometimes it'll be like, different methods of distribution, but like, what did I do wrong? And, no, people started to do it wrong, and people don't.